Recently, we were studying classification using naive Bayes. We saw how to classify using historic data set where all attributes are categorical. The data is discrete, like individual words in a message or different categorical values in the weather data set. We used the ideas about discrete probabilities and discrete conditional probabilities in order to provide naive Bayes model for classifying new records. How did we do that? For each class, for example, yes or no, we counted the number of values for each categorical attribute. Based on these counts, we computed discrete probabilities, probability of evidence 1 given yes, probability of evidence 1 given no, and so on. Based on Bayes' theorem and the assumption of conditional independence between all these evidences, we compared probability of E1 given yes, probability of E2 given yes, probability of En given yes, multiplied by prior probability of yes, and compare that with probability of E1 given no, probability of E2 given no, probability of En given no, and prior probability of no. And now, by comparing those two expressions, we were able to classify new record into one of the available classes, in this case, yes or no class. Let's look again at our favorite example, the weather dataset. First, we computed the prior probabilities of class yes and class no by counting the total number of yeses out of 14 available records. There are 9 out of 14 yes and 5 out of 14 no. Then, within each class, we counted how many times it was sunny. How many times it was sunny within the class yes. Out of all 9 yeses, the sunny was only in 2 cases. So the probability of sunny given yes is 2 out of 9. Similarly, we find how many times the day was sunny out of all available 5 no's. 3 out of 5. In a similar way, we counted how many times the windy was true out of all available 9 yeses, and counted how many times windy was true out of all available 5 records with the class no. We can also apply Laplace correction if required. Once we have all these discrete probabilities computed, we can compute odds of yes versus no given the evidence. The probability of yes given the sunny and true versus probability of no given sunny and true. So we compute that and then we determine what day that should be when the outlook is sunny and the windy is true. Yes or no, play or not play. Today, in this lecture, we will look what happens with our naive Bayes classifier if the attributes are numeric and continuous. Before you begin listening to this lecture, please review the lecture about continuous probability distributions, the previous lecture, please. Now, we are no longer dealing with discrete probabilities. That means we cannot just count the occurrence of a numeric value. But, however, we can use the continuous probability distribution. We can estimate the probability of observing some numeric continuous value E1 in class yes and in class no, and compare those probability estimations. Continuous numeric values follow some probability distribution. Let's say that they are normally distributed by their nature, such attributes like weight, height, etc. Say the values of attribute in class Y are normally distributed around some mean and with some standard deviation. And the values of the same attribute in class No are also normally distributed but have different mean and different standard deviation. If these two distributions differ, then we can use the values of the PDF function to see what is more probable, observing X given Y or observing X given No. For example, X1 definitely suggests that it has a much larger chance of happening inside class Y, and X3 has a larger chance of happening in class No. And if we observe the value X2, then the probabilities for both classes are roughly the same. While we know that the absolute likelihood or probability for a continuous random variable to take any particular value is 0, since there is an infinite set of possible values to begin with, the value of the PDF can be used to infer in any particular draw of the random variable how much more likely was drawn based from one distribution or based on another distribution. When we look at the formula of the probability density function PDF for the normal distribution, we see that for each value of x, it gives us some sort of probability of this x being in interval. See? From A to B. We also see that the function has two parameters, mu and sigma. If we make the interval very narrow, say epsilon in width, we can approximate the probability of x being in this very small interval by multiplying the value of PDF by epsilon. We kind of replace the area under the curve with the area of a very narrow rectangle. And then, if we want to compare posterior probabilities given different classes, we can just compare the values of the PDF function for each distribution. Again, we are computing the odds and the epsilons will cancel out. From the above discussion follows that we can use just the value of the PDF for a given value x for two different distributions, class Y and class N. In practice, to compute it, we need two parameters, mu and sigma. We need to know the two parameters of each distribution within each class. These parameters are computed from data by approximating the mean with a sample mean and by approximating the variance with a sample variance. Let's go over the example of such a computation, and let's begin by looking at a single numeric attribute called temperature. We will consider one evidence at a time, like we did before. We're observing some temperature and we want to find out what is more probable given this temperature, to play or not to play. Let's slightly modify the PDF formula and take this sigma in the denominator and put it inside the square root. If we do that, then we would need only to compute the mean, which is mu, and the sigma square, which is a variance. We do that based on a sample, while we take only the values inside class yes. So inside class yes, the mean of temperatures is 73, and the standard deviation is 38. So we obtained the PDF function for this specific distribution. You see, it's in blue. This is PDF function for temperatures inside class yes. And now, given that we know what is the temperature today, which is 66, we're trying to find out what is approximate probability of observing this temperature inside class yes. We find out that approximately this probability is equals 0.034. We compute the mean and the variance using the same exact formula, but now within the class no. And we estimate the probability of observing temperature 66 in class no, which is equals 0.026. Now we use Bayes rule to compare probability of class yes given temperature 66 versus probability of class no given the same temperature. Okay, and then as always from the odds ratio we can compute actual probabilities. Now let's generalize this idea from one numeric attribute to multiple attributes. If we naively assume, as before, that all these attributes are conditionally independent given the class, then we can multiply multiple probability estimators for different attributes. Moreover, because we are estimating the odds, we can combine probability estimates for discrete and categorical attributes into a single product and then use this product if we continue to believe that they are all conditionally independent. Let's see how this naive classifier will work for the full example of the weather dataset, where there is a combination of continuous numeric and categorical attributes. So we have this historic dataset, and we also have the new day, which we want to classify into one of two classes, to play or not to play. In the previous slides, we already computed both discrete probabilities for discrete attributes and also the probability of observing temperature 66 given class yes and given class no. What remains is only to compute the probability of observing humidity equals 90 within class yes and within class no. We do it using precisely the same procedure. We compute the mean within class yes and we compute the variance within class yes. And then we get the density function for humidity distribution of humidity in class yes. We do exactly the same thing for class no, and we find out the following two probabilities. Now we have everything we need in order to compare the probability of yes given this set of evidences versus probability of no. Naively assuming that all these attributes are conditionally independent, we just multiplying those probabilities and multiplying them by the prior probabilities of yes and no, and we getting the following proportions. See, denominator we do not need to compute, of course, because when we're doing the odds ratio, this p of the evidences will cancel out. And we find out that the actual probabilities of playing is 22% versus 78% of not playing. We're classifying the new day as a non-playable day. The next example is an exercise where you can exercise everything you learned so far. We have here a combination of two categorical attributes and one numeric continuous attribute, such as taxable income. And we want to predict if this person, if the new person, which is didn't get the refund, which is married and has the taxable income of 95K, if this person will evade taxes or will not evade taxes. So in this example, when we computing the probabilities of discrete attributes, we can apply Laplace normalization. And you already know how to do that. So once you finished the exercise and compute the probabilities of this person of evading taxes versus not evading taxes, then you can go to the next slides and compare your solutions to the one posted here. Summary of this entire lesson. If we have continuous numeric attribute E1 that follows some continuous distribution, and the parameters of this distribution are different for different classes A and B, we can use the PDF equation of each class to estimate the probability of observing E1 within class A versus probability of observing E1 within class B. For a categorical attribute E2, we already know how to estimate the probability of E2 given class A and given class B based on counts. If we naively assume that all the attributes are conditionally independent, we can use both these probabilities to discriminate probability of class A given these two observations versus class B given the same observations using the usual naive Bayes logic.